So, first part of thermophysics is all about temperature. So let's say we've got two objects. One object is hot and the other one is cold. So thermal energy moves from a hotter object to a colder object. So what will happen is the temperature of the orange object will go down and the temperature of the cold object will go up. And they'll keep doing this until there is no flow of energy between them. At that point, we say that both objects are in thermal equilibrium. The definition for that is when there is no net flow of thermal energy between two objects. It also means that both of the objects are at the same temperature. So what we're going to look at now is the absolute scale of temperature, which talks about a different unit for temperature. So we've been using degrees Celsius mostly to measure temperature, but you can also measure it in another unit known as Kelvin, which is signified with a capital K. And Kelvin is based on something called absolute zero, which is basically minus 273 degrees Celsius or 0 Kelvin. And it's basically the lowest temperature that's physically possible. So it's basically the lowest limit of temperature, so nothing can be colder than minus 273 degrees C or 0 Kelvin. This is the temperature at which a substance has minimum internal energy. So I'll explain what internal energy means in a second. But basically, if you increase the temperature from absolute zero, the internal energy of a substance also increases. And if you want to convert from degrees C to Kelvin, all you need to do is add 273. And if you want to go the other way around from Kelvin to degrees C, then you need to subtract 273 from it. So next up, we're going to look at solids, liquids, and gases. Okay, so these three diagrams show you how the particles in each of these states look like. So things you can say for solid. Particles in a solid are arranged regularly. They vibrate about their fixed positions. The spacing between the particles are small, and there are strong attractive forces holding the particles together. So let me just space these out a bit more. And if you increase the temperature of a solid, the vibration within the solid increases. Now for liquids, particles are arranged irregularly. Particles move freely in all directions. The spacing between the particles, they're still small. Compared to a solid, they're slightly more spread out, but you still describe them as being small. The attractive forces are weaker than a solid, but stronger than a gas. This time, as you increase the temperature of the liquid, the particles move around faster. Okay, gases. The particles in gases are arranged irregularly as well. The movement of particles are free as well. They move much quicker than liquid particles in all directions again. Spacing between the particles are much larger this time. So a lot of space, they're all spread out. All the particles are much more spread out. And there are weak attracting forces between the particles. And just like before for liquids, as the temperature increases, the particles move faster. Okay, so next thing we're going to look at is Brownian motion. It's basically a way of explaining how gas particles move around. A way to see this is to do the following experiment. So to observe Brownian motion, what you can do is you can get a microscope and you can look into a cloud chamber. So a cloud chamber is something that contains smoke particles and air particles inside. So let's take another view. So let's say this is the view of the cloud chamber from above. And what we observe are trails like this. You see little white streaks which take these zigzag paths. So this might be one, this might be another. And you see these forming all around the cloud chamber. And the key thing is that you have zigzag motion of smoke particles. You know it's the smoke particles because these trails are white. Now the question is, why does it show zigzag motion? And the reason for that is because, remember, it's containing smoke and air. So the smoke particles are moving around, but what's happening is the smoke particles come in contact with something in the air. And when it does that, it rebounds off it, it bounces off it, and then it changes direction. So that's why it's going straight here, then it rebounds and it goes in this direction, then it rebounds here and it goes slightly upwards, and every time it hits an air particle it changes direction. So that's why you get sudden changes in direction, which forms a zigzag motion. The reason why it makes a zigzag motion and you can't see what's causing it is because air particles are invisible. So two things you can conclude from this experiment are that the air particles travel in straight lines, because remember it's zigzag motion, they don't curve in between each change in direction, they travel straight lines, and the reason they change direction is because they're hitting air particles, and this whole motion is what we call Brownian motion. So next thing we're going to look at is internal energy. Let's start off with the definition for internal energy: the sum of the random distributions of the kinetic and potential energies associated with the molecules within a system. So what that means is if you have a gas, then the internal energy is the total energy when you add up the total contributions of kinetic energies and the total contribution of potential energies. And each one is caused by different things. So it's the total of kinetic and potential energies. The kinetic energy happens because of the vibrations of the molecules, so how much they vibrate within the substance. So the way you can increase the kinetic energy within a gas, for example, is to increase the temperature. So this depends on temperature. So for potential energy, this is due to the attractive forces which holds the molecules together. So if anything was to change with the attractive forces between the molecules, then the potential energy will change. So this could be something like changing state. So this depends on the bonding forces and the separation of the molecules. So to put more simply, you can say that the internal energy of a system is the sum of the kinetic energies and the potential energies. So if you want to increase the internal energy of a system, there's two ways you can do this. First way is to supply heat to the system, and second way is to supply work to the system. So by supplying heat to the system, you're basically increasing the kinetic energy of it, and to supply work, you're increasing the potential energy of the system. So next thing is specific heat capacity. Definition is the energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin without a change in state. So the equation for this is energy is equal to mass times specific heat capacity times change in temperature. So this is an equation that you would have come across in GCSE physics. E is energy measured in joules, M is mass measured in kilograms, specific heat capacity is C, is measured in joules per Kelvin per kilogram, and delta T is change in temperature. That's measured in Kelvin, although if it's measured in degrees C, you don't need to convert it because it's change in temperature. It's not just temperature. Okay, so one particular value you need to know is the specific heat capacity for water is equal to 4,200 joules per kilogram per Kelvin. So that's one to memorize. And basically what this all means, the definition, is that if you have a material with a high specific heat capacity, it basically means it's harder to raise its temperature. So the higher the specific heat capacity, the more energy you need to raise the temperature of that substance. So now an experiment that you can do for this. So let me explain what we have here. So in the middle here you have a metal block. So all of this represents a metal block. In that metal block you have a hole where you put a heater into it. That heater is connected to a circuit. You control how much heat energy transfers to the heater by changing this variable resistor here. Then you can measure the current and the potential difference using the ammeter and the voltmeter. So what's going to happen is you turn on the heater, and what that's going to do is it's going to warm up the metal block, and then you can record the temperature change because the thermometer is also within the metal block. To reduce any heat loss to the surroundings, you have insulation. So this is insulation around the metal block. And what you do is, first of all, measure the mass of the metal block, then measure the initial temperature, then turn on the heater and start a stopwatch. So that's probably an additional piece of apparatus you should add. Then you wait for the thermometer to rise to a particular temperature, and then once it's reached a particular temperature, you stop the heater and you record the final temperature. At that point, you should also stop your stopwatch, and then once you've done that, record your voltmeter, ammeter, and stopwatch readings. So remember, we're trying to work out the specific heat capacity. So we're going to use the equation E is equal to mc delta T. Now, we rearrange that to get C is equal to energy over m delta T. So if we want to work out the specific heat capacity of this metal block, what we need is mass, change in temperature, and energy. So mass is straightforward. We weighed that right at the start. We're using a balance. Change in temperature you do by subtracting the final temperature by the initial temperature. And to work out energy, we've got the voltmeter reading, the ammeter reading, and the time. So you need to use the equation from electricity. E is equal to VIT, or energy is equal to power times time, if you know that power is equal to IV. So this will give you your energy reading. You've got your mass reading, you've got your temperature reading, you put that all into the equation, and then from that you can get specific heat capacity reading. So that's an experiment to work out that. Now this is for a solid metal block. Sometimes they might ask you to work out the specific heat capacity of a liquid. The process is pretty much the same. It's just instead of a metal block, you might have a beaker with a liquid inside of it. You put the heater inside the liquid, you put the thermometer inside the liquid, insulate your beaker, and then do exactly the same process. So it's pretty much the same for both solids and liquids, it's just one small difference. Another thing that's important, especially if you're doing liquid, is you need to make sure that your liquid or solid doesn't change state. Remember, the definition for specific heat capacity is amount of energy required to raise the temperature by 1 degree Celsius or 1 Kelvin, but the state must not change. So that means you have to keep it the same state. So if you have a beaker of water, you can't let the water boil, and this is a metal block, but if it wasn't metal, then you can't let this melt. Otherwise it won't give you an accurate reading. So next thing is specific latent heat. This is all to do with the amount of energy required to change the state of 1 kilogram of a substance. So there's two different types of specific latent heats. One is changing the state of a substance from solid to liquid, and the other one is changing the state from liquid to gas. The first one we're going to look at is the one that changes the state from solid to liquid. So that's called the specific latent heat of fusion. And the definition is energy required to change the state of 1 kilogram of a substance from solid to liquid at melting point. So that last bit is important, is at melting point, because the temperature should not change during this process. So it's different to specific heat capacity, where the temperature does change but the state doesn't change. But specific latent heat, the state changes but the temperature doesn't change. The equation is energy is equal to mass times the latent heat of fusion, and latent heat of fusion is measured in joules per kilogram. Okay, so the second type of latent heat is specific latent heat of vaporization. The definition is very similar to what we had for fusion. The difference is the energy required to change the state of 1 kilogram of a substance, this time from liquid to gas, and it happens at boiling point, not melting point. Similar equation is just instead of latent heat of fusion, you have latent heat of vaporization. So with this comes a graph that explains how temperature changes when an object is going from solid and is being heated up with a constant supply of heat until it reaches a gas. So that graph looks something like this. So consider a block of ice being heated with a constant supply of heat until it turns into steam. So down here is the ice, the temperature is below 0 degrees. So let's say 0 degrees is around here. So it might be minus 20, it's being heated at a constant supply. So what happens is, because there's a constant supply of energy being added to the ice, it's going to rise up at a constant rate, hence the straight line. During this process, it's staying at the same state and it's rising in temperature. So due to the specific heat capacity, it's going to be increasing in temperature because all of the heat being supplied is going to increasing the temperature of the ice. But what happens is when it reaches 0 degrees, there's a change in state. It's going from solid to liquid. So the energy is being used to break apart the molecules so that it goes from solid to liquid. So at this point here, the energy is being used to supply the specific latent heat of fusion. So in the first stage here, it's completely a solid. In the second stage, it's going from solid to liquid. It's melting, so it's solid plus liquid. Then here, after all of the solid has melted to a liquid, the liquid starts to rise in temperature. So the energy being supplied is being used to increase the temperature of the liquid. Then eventually the liquid will reach 100 degrees C and it'll start to boil. And when it boils, again, the energy being supplied is being used to satisfy the specific latent heat of vaporization this time. So what you have here is a mixture of liquid and gas. And once all of the liquid has turned into gas, any extra energy being supplied goes into increasing the temperature of the gas. So when you do calculations with this, you need to know which equation to use at what stage. So if you have a solid which is increasing in temperature by staying as a solid, you would use E is equal to mc delta T. If you're looking at the process of melting, then you use the equation E is equal to m times latent heat of fusion. If you're dealing with just liquid, so again it's staying at the same state but it's increasing in temperature, then again you use E equals mc delta T. Now if it's boiling, you use the equation E is equal to mLV, latent heat of vaporization. And then if you're dealing with gas, again it's the same state, so if the temperature is increasing, E is equal to mc delta T.
For more videos like this, summary videos, worked examples and exam tips, subscribe to my channel.